proportional. Okay, so the lengths are proportional and the angles are congruent. Okay, so similar figures. So I'd write that down somewhere. Similar figures have congruent angles and proportional sides. All right. So there are certain ways that triangles can be similar. If you were trying to prove that, you would have to know what method you're going about that in. There's angle, there's side, and there's side, angle, side. Doesn't really necessarily matter if you know those for what we're doing here. We only have two triangles in the picture. Okay, so when we look at those, we can come up with the ratios that we need and the angles that would create this being similar. So the information that it gives us here for this picture is that CD is parallel to AB. And so the notation for that is they put the little arrows on those, saying that those are parallel to one another. And what that does for us is it creates all those angles being congruent, is what that does geometrically, that this angle is congruent to that one, this one is congruent to that one. And if you were to measure those, they'd be darn close. I don't know if it'd be perfect or not. I can't remember when I drew that, if I made them perfect, but they're darn close, okay? So we get these similar triangles, and what we want to look at there is setting up in order to find out what this missing side here is. That's what our end goal is. So we want to talk about the similar triangles. So triangle, I'm going to call it EBA, is similar to triangle EDC. In geometry, there's a notation that we use for this. It's just a little squiggle mark there. That little tilde or squiggle is the similarities mark. If it had an equal sign under it, that's the congruent mark. You take the equal sign away, it's a similar mark. Okay. Now, why did I write them in that order? Okay, yeah, the points as you travel around the triangles, they match up. So this angle right here matches this angle right here, and then this angle matches that angle, and then this angle matches that angle. So it follows around the triangle. It also creates this proportionate side idea that side EB relates to side ED. That's the relationship going on there. Side BA relates to side DC. Out of that. That's with the similarity statement. That's what's happening with this. Okay, so what we want to set up is that proportion in order to solve and find out what x is. So it's a little bit of algebra because we're using x, but in an elementary class, you're going to put an empty box there probably. So it's the same idea. You're about to say something. You were? Because it said algebra?
Yes.
Oh, you are. Have you got a fever? Oh, bless your heart. I will have to. A million bonus points to you. You wish that was true. All right, so setting up the proportion here. Let's get our relationship that we know. I always start with the smaller triangle on top, just because that makes a normal fraction to me. So the smaller side, if I pick 12 to go on top, what should go on the bottom from the bigger triangle? 30, the side that corresponds to that. X is on the smaller triangle. I'm going to use it. And then what side corresponds to that? 18. So we set up our proportion in order to solve for X. Okay, and this is what I would do if I were, if I'm in geometry class in high school, which we did this today, so I'm pretty good at it. I've been working at it all day. So 12 over 30 will actually reduce, right? To what? 2 over 5. All right, so 2/5 is equal to x over 18. How do you solve that? Cross multiply. So that's cross products, which would be a probably 6th, 7th, and 8th grade math standard, talking about cross products. And so that'd be 5x is equal to 2 times 18, which is, excuse me, 36. And then we would divide by that old 5 there. And we'll go ahead and do a decimal there even, because it terminates real nice, 7.2. And this would be millimeters because that's what it was measured in the original picture there. I wonder how to scale that is. I'm just curious. Not very much. It's nowhere. It's not near 7. So, I thought, man, that'd be cool if it was, but it's not. Does that make sense? Y'all remember doing that at some point in your life? Yeah, fun stuff. Good stuff. I'm with Maggie. It's fun. All right. Look at number dos. IJ is parallel to GH. So IJ is right here. My scan there didn't do too great. So IJ and GH are parallel to one another. I'm going to put the little marks on them saying they're parallel because I like to do notation on pictures sometimes. All right. And we want to get similar triangles. Well, there's only 2 triangles there, right? Triangle FIJ has got to be similar to what triangle? FGH. Good job. Got to follow it around the picture the same way. All right. So we need to find. Excuse me. We need to find x, which is x is not a side of a triangle. Right? That's what makes this one a little bit more difficult. So we want to set up our proportion to be able to do that. So what sides of the 2 similar triangles do we have that make up the first half of the proportion? IJ matches up with GH. So we have 20 over 26. Is that 25? It is 25, isn't it? I am. Although I'm not as blind as my neighbor. They called us one night. We were out, wife and I were out on a date, and they called and said, "Is everything okay?" And yeah, we're fine. Did you hear about this? And UPS had dropped a box off at her house, and her neighbor thought it was an ambulance. And like he swore he saw an ambulance leave our home, and it was UPS. So I'm not as blind as he is. I win on that. All right, so set up the other proportion. There you go. 18 is the side of the small triangle. And then the side of the big triangle that goes with it is this whole side from F to H, which would be 18 plus X or X plus 18. I don't really care how you do that part there. It doesn't matter. But what can I do to the left-hand side to make my life easier? Reducing fractions, which is always a fun thing to do. So that's 4 over 5. 18 over, I'm going to make it X plus 18 just to change it up. And then I'm doing my cross product. 5 times 18 to be 50 and 40, which is 90. And then 4x plus 40 and 32, 72. So distributive property there, which is a whole algebra concept, but definitely probably 6th grade standard. Minus 72. 18. 18 over 4 reduces to be 9 over 2, which is 4.5, right? 4.5 centimeters. Not crazy hard stuff we're doing this week. Really nice, easy things. All similar figures. Questions about the triangle stuff, number 1 and number 2 there.
Do we have to explain why they're similar?
The similarity statement does that for me. I'm okay with that. You know the rules for being similar that we wrote up here, that similar figures have congruent angles and proportional sides. If you know that and you make that similarity statement, I'm good. That explains it to me for that. As we mentioned, final exam earlier, there are some final exam questions that I've seen in the past with 191 and 192, where it's actually not working a problem. It's explaining why things are the way they are. And this would be one of those things. It'd be how are figures similar, might be what they ask. And you're supposed to somewhere on there be writing that similar figures have congruent angles and proportional sides. And there's actually no problem to work out of that. So just knowing that similarity statement though does it for me. I'm good with that. All right, let's get a big old word problem there. Small wildfire erupted in California. An aerial photograph shows the extent of the damage done by the wildfire tell I've been away for a minute. Okay. So it's done some damage before it was extinguished. The ranger evaluating the extent of the damage notes a burned truck in the photo and measures the length of the truck to be 6 millimeters. He knows the truck was originally 230 inches long, so he uses the measurements to estimate the burn area. In the photo, the burn area is roughly regular or rectangular and measures 16 centimeters by 7 centimeters wide. Approximately how many square feet were burned by the wildfire? And in the notes here, it says, careful, your units in this problem change from measurement to measurement. Okay, be sure that you're using consistent units in your calculations. However, it can be done without converting between the metric and customary system. Okay, so converting from metric to inches doesn't have to be done here because most of us don't know that. I could get close, but it probably wouldn't be perfect. Like an inch is 2.52 centimeters, something like that. But you don't have to do that for this problem. So we're going to try to set up here and figure out what's going on. So we know the measure of the truck is 6 millimeters in the picture. But in real life, this guy has seen this truck and he knows it's Chevy Silverado. It's 230 inches long in real life. Okay, so we have a ratio there, right? 6 millimeters to 30 inches. Okay. In the photo, in the burn area, it's rectangular, and the burn area measures 16 centimeters long by 7 centimeters wide. So that's a different dimension, right? So far, we've had millimeters to inches, and now we got centimeters by centimeters. Approximately how many square feet were burned by this wildfire? Okay. So square feet is a what? It's an area, right? The length of the truck is a linear distance, right? So area and linear distance don't always convert the same way. Linear distances convert with linear distances. So when we set up our proportion, we're going to have to set up a proportion that finds the length of the burn area and a different one or another one that finds the width. of the burn area. Okay, so we're going to set up a proportion to do that. Let's set up the proportion using the truck measurement first. And we've got to make a decision. We need to decide how we want to approach the millimeters and centimeters situation, because those are both in the metric system. So that would be an easy convert, right? To both being the same unit. From millimeters to centimeters would be easier. From centimeters to millimeters would be pretty easy. But either way there. So I'm a millimeters to centimeters kind of guy here, just to keep the numbers smaller. Because if I go from centimeters to millimeters, the 16 by 7 is going to get to be 160 by 70, which is bigger, big numbers. I'm going to go 16 millimeters is 0.6 centimeters, right? Because you remember on the rulers that we were using that a centimeter was this long, and the little marks in between, the 10 marks in between are millimeters. So there's 10 millimeters in every centimeter. So it moves the decimal place to the left once. So 0.6 centimeters is the same as 6 millimeters. That's going to help us. We still don't have to convert from metric to standard though. Okay. So when we set up our proportion for the length of the burn area, so I'm writing out what we're doing there. Length of the burn area, I'm on 0.6 over 230 inches. How long was the burn area in the picture? 16 centimeters. Where should that go on the other side? Top or bottom? And why? It'd be on top, not just because of the units, but think about how the left one is set up. It's picture over real life, right? So on the other side, it's got to be picture over real life. And we don't know how far that is, but we know it's some sort of inches. I'm going to call it X, because the X is a great variable. And we're just going to solve that. Cross product. Now everybody knows what 230 times 16 is, right? But in case you don't, I'm gonna do it with the calculator, because I don't know what it is either. 3680, of course. And then we're going to divide by 0.6. $61, 33.3 repeating inches. Okay. Let's get the width. Now set me up the proportion that I need to do for the width. Good job. So setting up 0.6 centimeters over 230. So the same scale that we learned from our truck that was in the picture, and then set it up with the other dimension, 7 centimeters over some sort of inches, and work it from there. 1400 and 210. 1610, is that how much that is? Yay. And then divide by 0.6.
1610 divided by 0.6. 2683. All right, so that gets us the inches of burn area in length and width. But let's go back to our problem, and what did they even ask for? Oh, that's not what I have. I have inches. And those are linear distances, not an area either. So how do I convert, and when do I convert here so that I can do the square footage of the burn area? All right, so that's a good question. What's a square foot? There's some around you. It's a block, right? It's a 1 foot by 1 foot area. Yeah, I think doing it before would be the best. You can be done afterwards, but I would say 1 foot by 1 foot is 1 square foot. But how many square inches is that? 12 inches by 12 inches is 144 square feet. So if you're going to convert at the end, you got to divide by 144. I think dividing by 12 is a lot easier, right? So converting right now would probably be the best bet. So we're going to convert this into feet. So I'm going to go to the calculator here. I'm going to grab that thing and divide it by 12. And then, so 511 does it say what to round to? Approximately. So we could go 1 decimal place and satisfy the approximately. That's 511.1 feet, right? And then take the 2683 divided by 12 and be 223.6. All right. And then the area equals length times width. For us, be 511.1 times 223.6. 511.1 times 223.6. 114,281. Square feet. $114,281, almost 282 square feet. That's a lot of space there. If you wanted to convert that into square miles, I'm just curious. Divided by 5,280. Oops. Divided by 5,280 squared, because that's how many. It's not that big, actually. Less than 4 1,000ths of a square mile. So it's kind of small. Maybe 114,000 square feet. Might be the size of this building, maybe. I don't know. The main part of the building, not counting the wing back here. Probably. But good conversions. But the fact that you don't have to convert back and forth between the metric there is a big thing. That it's proportional, even though the units don't match perfectly. If you had converted originally, you still get the same answer, but you don't have to convert there to make that happen. So keep that in mind as you're going along there. All right, so 22, check. Now let's get into the 3D figures. This is where everybody stinks at drawing. So playing field is equal. We all equally suck at drawing in 3D. Or maybe you're better at it than I am. I hope you are, because I'm not real great at it. But I can draw a little bit. So no explanations are necessary for the following problems. You never see that in Math 191 or 192, that you don't have to explain anything, but it's there, and that we're going to take advantage of that. Neatly draw the following figures by hand. You need practice drawing three-dimensional figures on two-dimensional paper. Then determine the number of faces, edges, vertices for each figure. Okay? What's a face? Yeah, like the wall. That's a perfectly good way of explaining it. It's like the wall. What's an edge? Yeah, the sides, the lines. And then a vertice, the points, the corners, right? In the room, you're in a three-dimensional room, right? That's a face. Where the walls meet in the corner, that's an edge. Where the corners meet the ceiling or the floor, those are vertices. So those are good ways to explain what those things are. And always, this is why we couldn't have class outside. It's because we didn't have any vertices or walls. We wouldn't have you either. Anyway, but those are good ways to explain those things. All right, so let's talk about a prism. A prism with a trapezoid for its base. Okay, so a prism, the way that works is it's a box, and whatever shape is the base is going to be on each end of the box. Okay, so it says a trapezoid is the base, and the prism is going to have a trapezoid on each end. And then the faces that connect those are rectangles. Okay, so we're going to try to draw a trapezoidal prism, is what the right word for that. So a trapezoidal prism. If you look at general prisms on your little handout here, there is one that is drawn there. Actually, it's on that page. The one on the right there is a trapezoidal prism. On your handout that I gave you, your reference sheet, the general prisms, the second one is a trapezoidal prism. That's what we're looking for. Yeah. So we're going to draw it on our. Yes, I do want you to do the dotted lines to show the faces and the edges that are on the back side. That's where it gets a little more difficult. No, the surfaces are the faces. The dotted lines are the edges that are like on the back side. All right, so let's draw. All right, so I'm going to draw a trapezoid. I'm just going to draw a trapezoid here. Doesn't have to be perfect trapezoid. It's a trapezoid. And then I'm going to take and I'm going to draw the same trapezoid back here behind it. So I'm just trying to draw the same shape. Yeah, I just and then here's the trick. Connect them. Corner to corner. You can draw it that way too. I'm just trying to show you ways to learn to do it better. That if you're not good at it, there are ways to get better at it. One of the easy ways to draw a three-dimensional figure is to draw the same shape twice. Like, did y'all ever do this when you were a kid? You did the cube thing? Yeah. And then you put the dot in the middle and you stared at it until it moved? I didn't do that. You did do that. Okay. If you do, it'll change the your. Does it?
Like this one, I think it's because
It's probably because it's shaded. Yeah, a little different axis.
This one sits on its trapezoid.
Right. The base, yeah, that's fine too.
So it doesn't matter.
It does. I'm okay with whatever orientation you put to it. I can usually accommodate that. But the key to a prism of whatever kind is it has that shape on each end. Whether that end is on the floor and at the ceiling, or in my case, it's at the front and the back. it's a trapezoid on each end there. And no matter which way you spin it, turn it, flip it, it's still a prism with the trapezoid on each end. Okay. How many faces does that have? You'll get better at it. It just takes practice. 6, because you got front, back, top, bottom. So there's 4. And then the 2 leaning sides is 5 and 6. So 6 faces. Edges. These are the lines. So we got 4 on each end. And then 1, 2, 3, 4 connecting them together. So that would be 12. Vertices. Those are the corners. 3, 4, 5, 6, 7, 8. All right. Just takes a little practice getting better at drawing these things and seeing 3D and 2D. All right, so let's look at number 2. We're going to draw a pyramid with a regular hexagon as its base. What's a regular hexagon? That's what regular means. All the sides are the same length. So we're going to draw a hexagon with all the sides the same length. What makes it a pyramid? It comes to a point. Okay, so we're going to make a hexagonal pyramid. So try to draw the hexagon with all the sides the same length. It doesn't have to be perfect. I don't expect you to be perfect. I am. My wife says I am, but I'm not. I'm just kidding. If she watches this, she'll shoot me. But she doesn't watch my videos, in case you're wondering. So I'm kind of trying to draw it, kind of laying down, similar to the one that's on this picture here. This is a square pyramid on your reference sheet. The gray part just needs to be a hexagon instead of a square. Okay. So the gray part that's in this picture, we're going to make it a hexagon. So I'm just going to try to draw a hexagon. I didn't do a very good job there. So I'm going to try again. Hexagon. Yes. That one in the back there. So that's a hexagon that I've colored yellow there. Hey, I drew it kind of flat. I'll start over. Kind of watch what I'm doing here. So I'm drawing 2 lines parallel to one another, like that, the same length, because it's regular. One, two, three. 1, 2, 3. I made a hexagon. I'm looking at it from the side. So that's why it doesn't look like it's regular, but it is. Okay. I'm drawing a pyramid, so I want my top up here kind of over the center of it. And then I'm connecting corners. And that one's kind of weird. Just the way it's oriented. I probably could spin it a little bit. Yeah, that back one there is supposed to be dotted. Because think about looking through the pictures, the one on the back side of the glass. You'll get kind of used to it. I don't know how to explain it. Honestly, as Coach Max says, I can't even see I don't know how to tell you how to see it. But hexagonal pyramid here. Number of faces. 7 faces. Number of edges. I got 12. Vertices. Got 6 around the bottom and 1 at the top, so it should be 7. Okay. All right. Number 2 says the number of faces, vertices, and edges for a prism whose base is an octagon. It doesn't say we have to draw it, but it doesn't say we don't draw it. You can draw it. If it will help you, draw it. I had a professor in, what was the class? Differential equations. Oh, God, that was a horrible class. But it's like Calculus 4. And he gave credit for good pictures. So whether you could do the math or not, if you drew a diagram that actually explained the situation, he gave you some credit for it. And thus I learned to draw a little better in differential equations than I could before I started that class. So, oh yeah, well, I'm gracious on the pictures. Don't feel like you've got to be perfect on them. I don't expect that. It just show me you're trying to get all of the important pieces. Here we're looking at a prism with octagons on the ends. And so how many faces would that have? It'd have 10 faces because you're going to have 8 around the outside and then the 2 octagons on the end. So that's 10. How many edges would that be? 8 on this end, 8 on that end, 16, and then 8 around. That'd be 24. Vertices. 8 on this end, 8 on this end, 16. And again, if you want to draw it, do that. You don't have to draw it to do this problem, but it could be might be useful to you to be able to draw that that figure. All right, let's go bigger. Determine the number of faces, vertices, and edges for a pyramid whose base is a 23gon. 24 what? Faces. Okay. Why? Explain to us why that's right. Yeah, you got a 23gon that's laying on the floor, and then there's 23 triangles that make up the sides of the TP. That's what I picture. Anytime I picture a pyramid, I picture a TP. Yeah, so 24 is the correct one. So number of edges. Because you got 23 around the bottom, and then there's 23 of the edges of that, so 46. Vertices. 24, because you got one corner at each of the sides, and then the one up the tippy top of the TP there. It makes that happen. Good job. So you're visualizing those 3D figures. That's next level. That's synthesizing on the Bloom's taxonomy. Good job. All right. Number 4, fill in the missing numbers in the following table. Show your calculations below. No explanation needed, but calculations might be. All right. So let's talk about what's a bipyramid. Yes, absolutely. Absolutely. So a bipyramid is, as Chris says, it's 2 pyramids where they're like that. So it's like the little symbol that's above your head if you ever played Sims. That's what they'll do. I played Sims. If you haven't, you're not missing anything. No. My sister-in-law was obsessed with it for a little while. She had a whole world. I think she lives in her own world now. Anyway, she doesn't watch my videos either, so I'm safe. So triangular bipyramid. So the bipyramid part is the part that sandwiches it together, but it's empty on the inside. Okay, so keep that in mind. Okay, so triangular bipyramid has 6 faces because there's 3 up top, 3 down the bottom. It's not a face on the inside because it doesn't have anything in there. Okay, how many edges does that have? So you got 3 around the middle where the pyramids are stuck together, and then 1, 2, 3 on the top side, 3 on the bottom side. So that would be 9 edges. Vertices, 3, 4, 5. Makes sense, but the vertices is a little easier. The edges can kind of get twisty sometimes. All right. Now, what's a pentagonal bipyramid? Absolutely, that's exactly right. It's just like that, except for in the center here, we're meeting at a pentagon. So 5 sides in the middle. So what does that do to the number of faces? Be 10, because you got 5 triangles that make up each the top and the bottom half of that. Or I guess 3-dimensionally, it would be hemispheres. It would be the right thing to call those. So that'd be 10. Number of edges, they were nice and told us it was 15. Why? Is it 15? Perfect. Good job. And the number of vertices is 7 because 5 around the middle, 1 at each end. All right. Gyro elongated square bipyramid. All right. This is a crazy shape. Y'all know what a gyroscope is? Okay, so it's a square bipyramid. So gyro elongated. Gyroscope is something that spins around, and and elongated. It just kind of makes stretches it out like that. That's a kaleidoscope that you're thinking about. Yeah, not the same thing. All right, so how many faces it has is 16. How is that? Just try to visualize what this shape does without looking it up yet. Mm-hmm. Now, Rubik's Cube is a cube. So, all right, so we got kinda. The gyro elongated is what kicks it here. So 4 on the bottom, 4 on the top gets you 8, right? So there's got to be 8 somewhere else. How's that happen? So let's try to let's Google that real quick and get the what that looks like. So gyro. I don't think I spelled that. Elongated. Square bipyramid. Weird looking shape. Okay. I don't know if I can. Trying to find. There's one on here that you can click on and kind of move around. And all right. So what you see out here beside that is the what's called the net of that. So they cut it open, and unfolded it. That's what they did with that. All right. So that's a dipyramid. We need a bipyramid. I clicked the wrong one. Bipyramid. Go back. That's what I want. Okay. So it's kind of crazy in the fact that it doesn't have, it has a square on each end. You can kind of see it. It's hard to see there, but look right here. There's where the square is for the pyramid. Down here on the bottom, it's right there. It's hard to, it's kind of hard to see, but the gyro elongated part is it inserts triangles in the middle of it, out of that. So it's just a weird shape. The idea of this is that you discover some things that you haven't talked about before in that. So gyro elongated bipyramid. So we got a bipyramid. We know that's where the 8 come from, but then these triangles that meet around the sides, that's the elongated part. 1, 2, 3, 4, 5, 6, 7, 8 more. So that's our 16 faces that we end up with. And then the number of vertices. So we got 4 around here, 4 around here, and then 2 more. So 8, 9, 10. Are we adding any vertices with these things? No, we're not adding any vertices with it. We're adding edges, but we're not adding vertices. So that's where the difference comes in there. So that should be a 10 there. And I'm not going to ask you a test question about a gyro elongated square pyramid, but the idea is that you think and use a little research to help you learn about that. So look at the next word. Very close. So rhombicosid dodecan. Okay, what's a rhombus? It's like a square get hit by a bus. Right? But what do we know about all the sides of a rhombus? They're all the same, right? Okay. And then dodecahedron. Y'all remember that from what is it? There's is it Alice in Wonderland that there's a dodecahedron in? Donald in Math Magic Land, if you ever Google that on the or hit the YouTubes for that one, they talk about the dodecahedron a little bit. But dodecahedron, let's Google that dude and see if we can get a picture of that. So the rhombicosid dodecahedron. There it is. Ooh, close. Not quite, but it's close. That one, the one at Epcot Center, is that the one you're talking about? It's got a few more points to it than this does, but this is definitely. So click here for a rotating model. That's the one I was thinking about was rotating. So you can see it spin. Kinda like a soccer ball. Soccer balls have pentagons and hexagons in them. This one has triangles mixed in with it. So it's similar to a soccer ball, same kind of idea out of that. So different kind of shape, weird looking, but it makes kind of a ball kind of thing. Let's kind of try to think about what's going on. Number of edges is 120. The number of vertices is 60. How many faces are there? So go back here to our info about this particular shape. And faces. There's one where they've colored all the faces. This is the thing cut open and laid out. Like if you took this and printed it out and cut it out of a piece of paper and then folded it at every edge, you'd be able to make that shape. This is called a net, and we'll get into these next week when we start. We'll talk about drawing nets. We won't do anything this complex, but we'll talk about nets for three-dimensional figures of it. This is the net for that. So how many faces are there? So that's how many sides are there. So
let's count up, I'm gonna count the pentagons, they're all in red, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 pentagons. And then, squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Did I count multiple
I
times?
think you did.
All right, start over then. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Got 30 again. Did I count them?
I know.
I think that's right that time, maybe. 30 squares. How many pentagons was it? 12? And then triangles. Twenty. Get 20 triangles. I see 3 on this node, 3 on this node. You got 22.
20 also.
20 off the It was there. All right, so 3, 6, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20,
Yeah, 62.
62 total.
62 faces. Fun times. Wow, fun times. That's cool. Enjoy looking at things I've not looked at before. Fun times. All right, let's go back to something a little more similar to what we're used to. You okay?
Where the problem says show your calculations below, that's just filling in the box.
Yes, yes. So if you had to add up, yeah, the pieces there, yeah. All right, 5. Figure below is the planar figure that can be cut out and folded to make a rectangular prism, also known as a net. N-E-T, not a net like Frankie and a net, but a net. N-E-T. Okay, so draw a planar figure that can be folded to make a prism whose base is a pentagon. Not to be perfect, just draw a reasonable representation. A planar figure to make a prism whose base is a pentagon. Okay? So key things here. What's a prism? What's a prism? It's a box with this one will have pentagons on each end, right? We're going to draw the planar figure. We're going to draw the net for this thing. Okay? Sometimes it helps to draw the figure itself first. So draw yourself a pentagonal prism. I drew myself a prism that is a pentagon on each end. Doesn't have to be just like that. It could be any shape. It could be a house shape. It could be some other pentagon. I just drew that one. Okay. So that particular net or planar figure needs to have what? Okay. So I'm going to draw a pentagon. Two, three, four, 5. 5 sides, right? And it will be connected to another pentagon via rectangle, correct? Now notice how this is not perfect. I'm doing that on purpose, right? Because I can't draw it perfect either. Okay. Now, what else do I need to add to this picture to make it build the prism. So how many rectangles do I need? And how big do they need to be? I need 4 more. And should they be the same size as this one in the middle or different? They should be about the same size as that because they're going to connect. Think about, I'm going to fold these two ends up and then smack them around the sides and make a box out of that. So I'm going to draw one here and then another one here. I could draw one down here if I wanted to. And remember, how many faces should I have? 7, right? Currently, I have 1, 2, 3, 4, 5, 6. I need one more rectangle. Doesn't matter where you put it there, whether you put it on top or bottom. 1, 2, 3, 4, 5, 6, 7 faces. I'm just showing that I'm counting that. You don't have to put numbers in them. But I would be able to fold that up and create that pentagonal prism. Yours doesn't have to be perfect, but it's got to have the basic elements of what we're trying to do here. Got to have the right number of faces. They got to be generally the correct shape. Measurements don't have to be perfect. Okay. B part says draw a planar figure that can be folded to make a pyramid that has an octagon as its base. Again, you must be perfect. Okay, so explain your visualization. Explain your vision there, young. It looks like the sun.
It does. You just have your octagon and you have your long triangle.
So you drew a regular octagon, obviously. Barely, something like that. Stop sign in the middle there. And then she said, oh, just got these beautiful rays of sunshine. You throw things at people? Don't mention that in your interview for being a teacher. I'm going to tell Mitchell. It's a ninja star. It's what my house does with ninja stars, not sunshine. Sunshine. Ninja star. Yeah, I agree. The pyramids are easier to draw than the others. The prisms are tougher because you got to spread them out more because they kind of unroll. That's done. That's it. That really is it on that. Because if you fold it up the sides, now, what if it was a cylinder? Okay, that face would be what shape? All right, you'd have circles on each end, and you'd have 3 faces really. And this face, when you unroll it, is a rectangle, right? What about a cone? That's the one. Okay, you got a circle as the base, and then to get it to make the cone shape, it actually you got a circle, and then the cone part would be circle, and then it's kind of a circular triangle, kind of like that. That's the only way to get it. Yeah, you just kind of cut it and unroll it, kind of thing. Think about unwrapping a Nutty Buddy ice cream thing. That helps me think of things. I always try to make it food for later. So pretty easy week here, guys. Homework from last week. If you can make me a stack up here before you leave and pick you up an assignment 21, 22, and 23. Pretty easy week, I think, anyway. Maybe easier than what we've had in the last month or so. And we will finish up geometry next week, praise God.